I'm an entrepreneurial fellow at Imperial College London, and I'm also a co-founder and the CEO of Solveteq, an Imperial spin-out company that is focused on battery recycling. But first and foremost, I am a battery scientist. My journey started in the late 2000s, just when the first Tesla Roadster and iPhone 3G were launched. I was then completing my master's project on electrolyte materials for lithium-ion batteries. These were very exciting times for battery researchers, and I personally wanted to be part of this rapidly evolving field. Fast forward to 2020, yesterday's future is today's present. Lithium-ion batteries are part of our everyday life, and today we have over 170 models of electric vehicles available on the market. At this point in time, we anticipate that the next technological milestones will include charging batteries within seconds, driving our electric vehicles for over 1,000 miles, and flying electric cars. And for myself, I continued pursuing an academic career and worked with some truly visionary scientists at the forefront of battery technology. However, while conducting fundamental research, it can be very exciting. It is not uncommon to lose sight of the bigger picture. The demand for lithium-ion batteries is growing exponentially. But where are the raw materials coming from? What is the product's impact on the economy, environment, and on society? Is all of this sustainable? Mining, processing, and recycling of battery materials in a sustainable way is critical for our ability to scale without on our planet and society. I felt it was time for me to broaden the scope of my research, and I became increasingly interested in the entire ecosystem of lithium-ion batteries. Specifically, I was curious to learn how spent batteries are being handled at their end of life. Until recently, recycling of lithium-ion was virtually non-existent. There were no major recycling plants and hardly any scientific research. The R&D was purely about making the batteries cheaper, lighter, and more efficient. Considering how lithium-ion has become so widespread and popular, I was surprised to learn that very little effort has been directed towards solving lithium-ion end-of-life issues. So about 2 years ago, I started looking for comparable examples of battery recycling, and I came across lead-acid batteries. These would be your typical 12-volt batteries, which can be found in every internal combustion engine car. Interestingly enough, not many people would know that lead-acid batteries are also used in every state-of-the-art hybrid and electric vehicle. Unlike with lithium-ion batteries, there is not much hype around lead-acid technology, mainly because it's been on the market for about a century. What is remarkable about this technology, however, is that 99% of these batteries are being collected and recycled at their end of life. In addition, all components of lead-acid batteries can be recycled and reused in a new battery. Did you know that 80% of your new car battery is made of recycled materials? This is outstanding, not only when compared to other battery technologies, but also in comparison to any other recyclable product. Their recycling rates exceed those of paper, glass, or aluminum cans, making lead-acid batteries the most recycled consumer product in the world. This is thanks to various factors: the infinite recyclability of lead, the cost of raw materials, the simplicity of the product, and the enforcement of environmental regulation. This market is considered a perfect example for circular economy. But it is not free from issues and challenges. We all know that lead is highly toxic. Exposure to lead affects all organs in the body and often causes irreversible health issues. Long-term exposure to lead can be associated with cognitive impairment, behavioral problems, lower IQ, increased societal violence, and lower life expectancy. Today, human exposure to lead comes primarily from informal recycling of lead-acid batteries in low and middle-income countries. And it is estimated that up to 30% of children around the world might be suffering from lead poisoning. For that reason, informal lead recycling is considered the most polluting industrial process in the world. The existing method of recycling of lead-acid batteries includes crushing, separation of materials, and smelting. Smelting is a high-temperature combustion process done at 1100 centigrade, and it is the most energy-intensive and polluting step in the whole recycling process. It is also the most expensive step, because if it's done properly, it may cost companies up to 40% of their annual expenditure just to comply with environmental regulations. At present, there is no industrial recycling process on the market that is both cheap and environmentally friendly. With that in mind, my colleagues and I have developed an alternative method to smelting. We do not reinvent the wheel, so to speak, but rather take out the most expensive, the most energy intensive, and the most polluting part of the process, and we replace it with our low temperature solvent-based technology. This new method allows recyclers to avoid the smelting step. In its essence, our patent-protected technology is using a special type of solvents called dipotectic solvents. We use them to recover lead from used lead-acid batteries. Dipotectic solvents are composed of low-cost, easily available, and benign chemicals, such as ethylene glycol. They have a low environmental impact and are easy and safe to handle. Most importantly, they have the ability to dissolve a wide range of lead compounds, including components of used lead-acid batteries, which are otherwise difficult to dissolve, or are even insoluble in other liquid media. Our process is solvent-based, so we produce significantly less hazardous air pollutants during the process. We also significantly reduce CO2 emissions, which together makes lead recycling more environmentally friendly. We also move from smelting at 1100 degrees to temperatures as low as room temperature, which reduces energy consumption and makes the entire process much cheaper than smelting. Finally, we are also faster because we require fewer steps to produce lead products that can be used in new lead-acid batteries. As I said, there is no lead recycling process on the market that is both cheap and environmentally friendly. But our technology has potential to address this environmental, societal, and economic issue. To fully maximize impact of our research at Imperial, my colleagues and I decided to set up Solveteq, a spin-out company dedicated to the commercialization of this technology. We work very closely with established industrial partners, recycling experts, and our future customers to meet commercial requirements. And this is a very exciting part of the journey for our team because it gives us an opportunity to look at our process beyond the laboratory scale. We analyze the economics of our process, or we develop the solvent recovery system to minimize the production of chemical waste. Currently, the technology is at the prototyping stage, and once the model is proven at industrial scale, the technology will be deployed worldwide. And while this is already greatly exciting, the future is even more interesting. It is widely recognized that climate change is the most serious and threatening global environmental problem. One of the ways this challenge can be addressed is by transition to a carbon neutral economy. And an increasing number of countries and organizations are already targeting net zero emissions by 2050 or even earlier. From a wider economy perspective, this can be done, for example, by moving away from fossil fuels to electricity generated from renewable energy sources, such as wind, hydropower, or biomass. Another option is reduction of greenhouse emissions generated by our transport system. EVs are a great option for reducing our carbon footprint in comparison to standard petrol or diesel engines. Electric vehicles market grows steadily in the last few years, reaching sales of 2.5 million units in 2019, which is slightly less than 3% of total vehicle sales. However, the real takeoff for EVs is expected to happen from the second half of the 2020s, when electric cars are expected to become cheaper to own than internal combustion engine models. The electric vehicle revolution is responsible for surging battery demand. Today, the size of lithium-ion market is driven by expansion of the plug-in hybrid and electric vehicle market. The increasing demand for lithium-ion cells is met with an increasing number of gigafactories, which are built around the world. Once the battery market moved to the economy of scale, we started to observe the drop in battery prices. This, as a result, makes the electric vehicles more affordable, which then further increases demand for batteries. This spectacular success of batteries and electric vehicles is expected to continue for the next 2 decades. This unprecedented demand can be only compared with the demand for oil in the 1910s and 1920s. One could ask then if batteries are the new oil. However, this success also puts an enormous strain on the entire supply chain. To meet this demand, we will need to produce more and more batteries. But we only have a finite amount of resources. If we continue expansion at this speed, we will soon run out of raw materials such as lithium or cobalt. Therefore, the real question here should be, are batteries the new oil or the new plastic? The answer to this question is around sustainability. We have to build our sustainability map for lithium-ion batteries, and we have to build it now. And we all have a role to play here, starting from us, material scientists, engineers, car manufacturers, regulators, all the way to all of us consumers. We can contribute to making batteries more sustainable. For the last few minutes, I will share with you how we material scientists address this problem. First and foremost, we shall make our batteries safer, more efficient, and last longer. For the first example, I've chosen a material that is responsible for making battery headlines in the last few weeks. It is a cathode material called NMC, which stands for lithium manganese cobalt oxide. These materials have a layered crystal structure, which allows a facile intercalation and deintercalation of lithium ions upon charge and discharge of the battery. The original layered material here was lithium cobalt oxide, and it was successfully used early on in small portable electronics. However, cobalt is more expensive and less abundant than other transition metals. Cobalt also presents political and ethical issues because of the way it is mined in Congo. As a result, cheaper cathodes have been developed to substitute some of the cobalt with nickel and manganese. These are used in the majority of lithium-ion batteries in electric vehicles. And it's done due to their high specific capacity, ease of production, and moderate cost. The material I want to mention to you is NMC 532, where 5, 3, and 2 corresponds to atomic ratios between nickel, manganese, and cobalt. It was produced as a single crystal, unlike other cathode materials, which are typically polycrystalline. This made NMC 532 extremely resistant to oxygen loss from the crystal structure, and as a result, lithium-ion cells with NMC 532 have an exceptional performance in terms of cycle life. These new batteries would last for over 16 years and over 1 million miles. This work was done by Professor Jeff Dunn and his group from Dalhousie University in Canada. Jeff is also known for his close collaboration with Tesla, which announced that they will be implementing a game-changing battery technology later this year. Another example of making batteries more sustainable would be solid-state batteries. In that case, an organic flammable electrolyte and graphite-based anode would be replaced with a ceramic electrolyte and a lithium metal anode. This would increase the range of the battery and address the safety concerns. Currently, research efforts are focused on discovery of the most suitable electrolytes that will be mechanically and chemically stable with lithium metal. And they will provide intimate contact with the active cathode material upon charge and discharge. But actually, I'm not sure if it's changing. Okay, great. But actually, there is already a battery technology on the market that works with metallic lithium. This is lithium sulfur battery, where an anode is made of lithium and a cathode comprises elemental sulfur. Both lithium and sulfur are extremely light materials, delivering high energy batteries. This is suitable for applications where weight is critical, for example, aerospace. Moreover, sulfur costs approximately $200 per ton, which is much cheaper than cobalt, for example. It is also much safer to work with, and there are no heavy elements involved, which positions this technology strongly on the sustainability scale. Then, we also have to look beyond lithium and lithium-ion. And there is currently a lot of work done towards new chemistries, such as sodium-ion or magnesium-ion, where materials are cheaper and more abundant. And of course, the sustainable recycling of batteries at their end of life. However, this is extremely difficult to establish at this point in time. We have a large number of different chemistries on the market. Elemental composition of batteries varies greatly, and there is no sufficient legislation in place to determine manufacturing standards, collection, or recycling. But for the time being, the clues are in the cost of lithium cells. What are the most valuable components? From this breakdown, one can see that over 50% of battery value is in its cathode materials: nickel, lithium, cobalt, and manganese. Not surprisingly, the most advanced method of lithium-ion recycling today is pyrometallurgy, where batteries are smelted, and they produce alloys of copper, cobalt, iron, and nickel. The slag from this process typically contains aluminium, manganese, and lithium, which can be reclaimed by further hydrometallurgical process. But electrolytes, plastic, and lithium salts are usually lost in the process. Despite environmental drawbacks, high energy costs, and the limited number of materials reclaimed during pyrometallurgy, this is a frequently used process to reclaim high-value transition metals such as cobalt or nickel. Hydrometallurgy involves the use of aqueous solution to leach metals from cathode materials, typically sulfuric acid and hydrogen peroxide. Subsequently, metals go through precipitation reactions to recover cobalt and lithium, or transition metals, or NMC. The big issues to be addressed with all hydrometallurgical processes are the volumes of solvent required, the speed of delamination, the cost of neutralization, and the likelihood of cross-contamination of materials. And direct recycling involves removal of cathode or anode material from used battery, followed by reconditioning and reuse in a remanufactured battery. For example, after dismantling used batteries, cathode strips could be delaminated in a solvent, powders could be recovered and regenerated, and lithium content could be replenished and compensated for losses during battery use. And finally, bioleaching. It's a method in which bacteria are harnessed to recover valuable metals, such as cobalt or nickel. This is a relatively new method, but has been successfully used in the mining industry. And it can be potentially complementary to pyro and hydrometallurgical processes. On this slide, I just want to share with you work published recently in Nature Energy, where depotectic solvents were used to successfully recover lithium cobalt oxide from used lithium-ion batteries, with efficiencies as high as 99%. Similarly to our work with lead acid, they also showed that it is possible to recover and reuse the solvents. So how will the sustainable battery market will look in 2040? EVs will make up the majority of new car sales worldwide, but we shall be prepared to be using air taxis by then. For every terafactory, there will be a tera recycling plant. Our batteries will be made from recycled materials, and if it's not possible, from materials that will be ethically sourced. We will have a range of battery technologies with their chemistries optimized for different applications, whether it is transport, stationary energy storage, or wearable electronics. The battery cells, packs, and modules will be designed to enable efficient disassembly, separation of components, and material recovery. Legislation-wise, there will be strict regulations about who is responsible for battery recycling. New ownership models will be in place. For example, we may only lease the EV battery pack from a car manufacturer, and they will determine whether the batteries will be repurposed at the end of life or recycled. And finally, coming back to lead recycling. I hope our technology will become a global standard for lead recycling, and we will eliminate lead pollution. Because it doesn't matter whether it is 30% or 0.3%, no children should be suffering from lead poisoning. Hopefully, this talk highlighted for you how important sustainability in energy storage is. Either these are lead acid or lithium-ion batteries. And what are the risks for not preparing for it? At the end of the day, it is our responsibility, either as academics or Imperial business partners, to build a better world after the COVID-19 crisis. A world that is cleaner, more sustainable, more energy efficient, and more respectful of the climate. Thank you very much.
Thank you so much for your talk. It was really insightful. I especially thought it was interesting to hear how we might in the future even share the way we see the ownership around batteries. So putting more of a responsibility perhaps on the car manufacturers. So I have a couple of questions that have come in from the audience ahead of this event. So the first one is, can we envisage the solvent-based recycling technology to be adopted to the point of use? For example, could we see battery recycling or refurbishment being done in high street shops, or maybe by consumers themselves? Oh, wow. I'm a chemist, so my first answer will be, don't try this at home. But so actually the solvents that we are using, they're really benign. They're not dangerous. Some of the components are used as food additives. So I'm not concerned about this too much, but batteries themselves, either lead acid batteries or lithium-ion batteries, they are made of toxic materials. And definitely nobody who's not qualified shall not try to play with it. They're also dangerous because, especially with lithium-ion batteries, what's encapsulated inside are volatile organic flammable solvents. So we really have to be careful. However, I do kind of get the point of trying to distribute points of recycling. At the moment, especially for, I can speak about lead acid recycling, it's dominated by economy of scale. So there are very few recycling plants. So for example, in the US, there are only 7 recycling plants in the entire country. So imagine about all this used lead acid batteries traveling by car to those recycling points. There is some good thinking in this, I agree. Fantastic. And there's a question that's come in from the audience today that's a little bit connected to this. So what do you anticipate being the biggest challenge in getting battery recyclers to ditch smelting and move to Solveteq instead? Do you think there will be much inertia to overcome?
It's interesting. I think it will be regulations. So we have constantly tightening environmental regulations, and that's for good reasons. And if I have to say there are several companies that are interested in changing to green solutions. If it's possible, obviously we have to prove they're economic, they're economical. But if companies have choice, you have people behind companies and they do care about the environment, they do want to do the right thing. And especially, and this supported with regulations. I think there is a change coming.
So do you think so what do you think is the biggest challenge at the moment for them moving to Solveteq instead? Is that changing the complete?
I think we're just too small and we are not ready yet. If we were ready tomorrow, that would be great. But we are a small startup, so trying to grow slowly. But actually for lithium-ion market, it's legislation and there is still no clarity what happens with used lead acid lithium-ion batteries, what happens with the batteries from our phones. And then very shortly we'll have an issue with all the batteries coming from electric vehicles. So we have to address it now.
Fantastic. And Nick Rimmer has asked, does Solveteq have a solution for lithium-ion batteries today? I know you shared a little bit of research at the end. Can you share a little bit more?
We are working on this, and that's definitely the next thing that we're going to be involved. And we are, I'm Faraday Institution Entrepreneurial Fellow, and Faraday Institution is the biggest funding body for funding energy storage research in the UK, and we are strong on this. There is a strong recycling project going on, so if you want to check it out, please go online and look it up.
Fantastic, and it's almost like watch this space with Solveteq as well. Then.
Please do.
So another question from James here is there a standard or potential basis for one which could be made law, which should be used or met for batteries in the circular economy?
Oh, so there are so many, it's difficult. There is no one, there are European Union regulations. So it's end of life directive for batteries that is being revised now, and European Union is trying to capture all different technologies in there. So hopefully there will be standards. There will be also local standards, probably our own standards in the UK. And then the market itself, I know about companies that are outside European Union, but their business partners are in EU, so they want to comply with these regulations. So they follow them, even though they're not required.
Do you think there is room for better laws and regulation then around circular economy, especially in concerns to batteries?
Totally, because there is no regulations on lithium-ion. That I think us as consumers, we really have to start thinking, where is this battery coming from? What happens with it when I change my phone and I ditch the old? Something that we may not, so I didn't mention the supply chain, but for example, problem with cobalt is that it might, having a phone, we might have somehow indirectly contributed to child labor, because the cobalt mostly comes from Democratic Republic of Congo. And then at the end, do we know what happens with our batteries? Are they probably, our electronic waste is probably shipped somewhere in Asia, and we are a polluting industry, even though on daily basis this is not something we would do, but we might unknowingly contribute to the problem.
And I guess it's something that was made even more clear after the COVID crisis as well, around supply chains and making it all in countries that are like trying to think about ways to decentralize both recycling, but also access to batteries.
So I can, so also I didn't have time to speak about supply chain, but at the moment lithium is coming, for example, from Chile, nickel is coming from Australia, and cobalt is coming from DRC. And they all go to China, where the lithium-ion cells are produced, then it goes to Korea, where the car is produced, and then it goes to the US or to Europe. And just by the time you receive the keys to your electric vehicles, imagine the carbon footprint of this. But there are changes in the market all over the world, and also in the European Union, and especially there is more focus on this. There are things happening, and they're happening really fast, and I'm really happy. So I look forward to those changes and having more transparency and regulations. And I think even at this point, the European Union is considering passports for the materials to actually know where they're coming from and where they're going. So that's something to look out for.
That's really interesting, with an increased transparency of materials as well. So I think we'll do one more question, which I'm actually quite keen on understanding a little bit more as well, which is another one from Nick Kramer, who asks, why haven't lithium sulfur batteries been more successful? They sounded very promising from your talk.
Ah, yes. I was thinking about it again the other day. I was like, oh, well, actually, not recyclability, their life cycle is not as good as for lithium-ion. So their life cycle is much shorter. Mm-hmm. So maybe not 1,000, 2,000 charge and discharged cycles are available. So they're really good for shorter use, but for very specific applications. But also in that space, there is a lot of research going on, and there are companies that are looking into it. And batteries are a very dynamic field, for sure.
Fantastic. Thank you so much for sharing your vision on the battery technologies and the future of the work that you're doing with Solveteq.